Hello, welcome to this presentation. My name is Samadian, and today I am going to talk about fatigue crack growth models in wire+arc additively manufactured components. The co-author of this presentation is my promoter, Professor Wim de Waele. We are both from Ghent University in Belgium. In this presentation, we are going to talk about a model which can predict the fatigue crack growth in a wire+arc additively manufactured made component. This presentation contains 4 sections. Firstly, I'm going to briefly explain about the method, and then our experimental study, then briefly about the finite element model used for stress concentration factor extraction, and finally our unified fatigue model, which we developed for this purpose. Wire+arc additive manufacturing actually is very similar to welding. Here we have an automatic welding power source, a torch, a wire feed system, very similar to welding, and a robot arm which moves and manipulates our torch. The way it works is that the position of the layer on the layer or of the metal can be steel, aluminum, titanium, name it. There are lots of publication about the different material used in this with this method. The good features of wire+arc additive manufacturing is its high deposition rate. Therefore, it's very good for large component production and also for repair. Therefore, we have a low price and also commercial abundance of filler wire, since the method is quite close to welding. But there are also certain limitations with wire+arc additive manufacturing. The most important ones are low dimensional accuracy and also the poor surface finish, which we refer to as surface waviness. And also we have a high residual stresses. Here you can see some of the examples from the components which have been made by WAM, a rocket engine and a bridge. A WAM-made component inherently has a very rough surface. Normally, we refer to them as a waviness. The solution for these wavinesses normally is post-deposition machining. Post-deposition machining, however, imposes extra costs on the production. Often it's not feasible and can nullify some of the advantages gained through the additive manufacturing process, like optimized designs. Therefore, an optimized post-process treatment in which machining can be prioritized for critical location is in great need, particularly for components under the fatigue loading, because we know these surface waviness can be very detrimental for fatigue life. Therefore, we conducted this research in order to having a clear and profound understanding about the effect of surface waviness on fatigue performance, and we believe this can significantly contribute toward the formulation of such optimized procedure. Okay, let's take a look on what we have done in the laboratory for this project. In the experimental phase, a few single-layer valves were manufactured with a Fronius CMT power source and a Panasonic robot arm. As you can see, one of those at the middle of this slide. A robot in OCA's facilities in Belgium has been used for this purpose. Experimental campaigns contain tensile, Sharpie, hardness, and fatigue tests. But since we are here only focused on fatigue properties, I showed the fatigue samples only. 6 samples in total were manufactured. 3 of them had only a one machine surface, and the other surface of them were kept as built. F1, 2, 3 at the left side are as-built samples. The other batch had the 2 machined surfaces, F4 to F6. Nonetheless, the thickness of all samples were equal. In this study, we use a special technique to derive fatigue properties, which we refer to it as a fast fatigue determination technique. In this technique, we use the infrared thermography camera to monitor the temperature evolution during the fatigue test. Using this technique, we can determine fatigue limit as well as S-N curve in relatively shorter time and with less samples. Actually, we use 3 samples instead of 10 or maybe 20 samples, which would be normally required in a conventional method for such a test. On the left-hand side, you can see the setup that we used contained the IR camera, samples between 2 clamp, and curtains, which we use to isolate the samples from the environment in order to avoid the effect of environment temperature fluctuation on our measurements. On the right-hand side, you can see the samples through our IR camera, and in the bottom, you can see a red spot showing the initial crack stage, and also you can see a reference sample that we use in order to have a reference temperature which shows the environmental effect on exactly the same material, size, and dimension. Here you can see the final result of our test and the constructed S-N curve, which is estimated using the fast determination technique. And it's obvious that almost the machined specimen has a 2 times higher fatigue limit compared to the as-built samples. So machining could increase the fatigue endurance limit almost 2 times. And then we can understand that how significantly can these rough surfaces can be detrimental for the fatigue limit. Obviously, the main suspect here is the stress concentration at the surface due to the waviness. And therefore, we decided to dig a bit more in this subject and try to see the effect of the stress concentration in more details. Let's take a look how we derive stress concentration factor out of our finite element model. In this study, we imported data point by point from experimental measurement to our finite element model. However, before doing that, we needed to know where are the most critical points to refine the mesh in those regions. To approximate these critical points, we use fast Fourier transform. Since any surface profile theoretically can be approximated as a sum of many sinusoidal waves with different amplitude and frequency. And as a result, we can describe the surface mathematically with a Fourier transform. As you can see here in the right-hand side graph, the blue graphs show actual profile and the red graphs are the fast Fourier transform approximations. From top to below, by increasing the Fourier components quantity up to 1000, you can see that we could achieve almost perfect agreement between the actual profile and our Fourier-based approximation. In order to construct the finite element model, knowing the critical locations from Fourier approximations, meshes are refined in critical sites, normally in the valleys. Then, by applying axial force at the 2 sides of the model, we compared principal stresses at the valley with the nominal stress applied far from that critical locations. And that's basically our stress concentration factor. To derive the stress concentration factor, the values of the principal stresses at the critical locations are averaged in a certain region coming from the critical distance theory, and then we calculated basically the stresses at every element and then take the average of all those elements in order to ensure that our measurements are not affected by the mesh size. And finally, our unified fatigue model. Fatigue crack growth is normally categorized into 2 regimes, long crack and short crack. In the long crack regime, it is assumed that the growth is governed by the Paris law, and there is a constant threshold for crack propagation, delta KTH. So that means that when the delta K is less than a delta KTH, no crack propagation happens. However, it is proven that in reality, even in the smaller stress intensity ranges, crack not only can grow, but also grow faster than expected. So while in long crack regime, the stress intensity factor threshold, delta Kh, is independent of the crack size, in a small crack regime, this becomes crack size independent. Defining AD as the crack length below which the fatigue threshold is no longer crack size independent, then the variation in stress intensity factor for fatigue can be actually expressed as a function of crack length. This can be explained better by Kitagawa-Takashi diagram. They show that experimental data could be described by two lines, one representing the plane specimen fatigue strength, CL delta sigma fat, and the other is the linear elastic fracture mechanic prediction using the crack propagation threshold delta KTH. To describe the KT diagram, normally two models are used, Chapati and Al-Haddad. Here we use Al-Haddad model, and as you can see in the right hand side, in Al-Haddad model we can define delta KTH length dependent, delta KTHA, as a function of delta KTH and length of the crack and the critical defect size, AD. AD by itself can be described by A0 and beta. Beta is geometric function, and then A0 is the material critical distance defined in the lower line. We constructed our model assuming a pre-existing defect in one of the most critical locations, and assumed it would grow in two directions, through thickness and along the surface. The stress concentration factor Kt is defined as ratio of the local stress at the valley to the nominal stress. Then basically we can say that in true thickness direction, probably stress concentration factor has a very marginal influence on the crack growth. However, it can affect the surface direction growth significantly. On the other hand, we can hypothesize that the ratio between the fatigue limit of a machine sample to its rough as-built counterpart is basically stress concentration factor. Because, assuming the linear elastic fracture mechanics framework, the threshold which controls gross onset of a crack is stress intensity factor K1. And in this case, the only difference between the two samples is the local stress, which is controlled by the stress concentration factor. Let's take a closer look at what we have for a fatigue limit and threshold for a specimen with a rough surface. We can assume that if the crack size was infinitely small, basically almost zero, the fatigue limit, the threshold of the fatigue crack growth is equal to the fatigue limit. And since we can express the fatigue limit as a function of the smooth fatigue limit and the stress concentration factor, as I explained before, we can write this formula. And from this, we can actually derive our A0 prime new intrinsic length as it is. And then assuming the same type of relation that Al-Haddad assumed for A0, we can basically write our A prime 0 as a function of A0, and we can call it A prime D, which means A prime D is equal to the square of the stress concentration factor and AD, same AD as Al-Haddad assumed. Having this in mind, we can basically define the new crack length dependent threshold for a specimen containing surface waviness. Using these new assumptions, we can then update our model in a way that the growth in a true thickness direction, delta A prime over delta dn, has a length dependent threshold, and then the growth through over a surface, delta C prime over dn, has the effect of the stress concentration factor as a KT directly multiplied to the delta K. The effect of the surface waviness highlighted by unified models are twofold. First of all, as AD prime is always larger than AD, more crack growth will be required before the transition to long crack regime occurs in wavy surfaces. The second effect is that the surface waviness model will predict an increased propagation rate due to the reduced threshold, which means that the shorter cracks in a wavy surfaces grow faster than their counterpart in a smooth or machine surfaces. As shown here in a graph, it should be noted that since both thresholds, delta KTHA, which means that machine surfaces threshold, and delta KTH prime, rough surfaces threshold for short crack regimes, eventually converge to delta KTH, threshold of long crack growth after certain crack growth. The propagation rates in the through thickness direction will be the same for a long crack originating from a smooth or from a rough surface. In other words, the only differences that we assumed in our unified fatigue model is for short crack regimes threshold due to the presence of the wavy surfaces and due to the presence of stress concentration factors in a valley. To conclude, here I presented a framework in which we try to model the fatigue crack growth in short crack and long crack regimes. This framework contains experimental surface profile measurement, and then out of it we use Fourier-based analytical method in order to represent the surface in an analytical way. And once we have it, we use this representation in order to achieve a more optimized finite element model, which can be used to extract a stress concentration factor. Once we extracted the stress concentration factor, we could use that in order for our unified fatigue model to predict fatigue crack growth in short crack and long crack regimes. The next step of this project is comparison between our experimental measurement and this fatigue crack growth model. However, in experimental phase, we face certain challenges to measure the crack growth in short crack regimes. Thank you very much for your attention. I'm happy to answer your question, and also you can send your question to my email, which is mentioned here. Thanks again.